Lecture 4, Einstein, Measurement, and Meaning.
Having seen that it's no mean feat to settle on the essential features of science, we return to our previously scheduled narrative. We saw in Lecture 2 how an aspect of Einstein's general theory of relativity served as a kind of momentous and inspiring example of successful science for people like Popper. This time we jump a bit farther back in time to Einstein's special theory of relativity. The crucial paper was published in 1905 when Einstein was only 26. Now, this was an enormous breakthrough in physics, but we're going to be focusing on the philosophical implications, which are really no less enormous. Now, special relativity is indeed a wonderful theory, but special here means special case of, not specially wonderful. The special theory concerns motion at constant velocity, motion of objects not subject to any accelerating forces causing their speed or direction to change. I will sometimes call this inertial motion. The general theory of relativity applies to all motion, accelerated as well as constant motion. And so it's presumably the more special in the sense of wonderful of the two theories, since it covers all of the cases. We can stick for our purposes to the simpler case of special relativity. One noteworthy thing about the history of this issue is that some of the ideas most commonly associated with Einstein did not in fact originate with him. His genius, as we're going to see, consisted not so much in inventing the components of the special theory, but of reconciling them, which was quite the challenging task. Now, we're reasonably familiar with the idea that unaccelerated or inertial motion can be detected and described only with respect to some reference frame. Galileo, early in the 17th century, argued that objects will move the same way whether the experiment is performed on land or aboard a ship sailing at a constant velocity over smooth seas. Now, you know that this must have been a thought experiment since you can't get a ship to actually sail at constant velocity over smooth seas. But Galileo's point remains, you can feel it if the ship changes speed or direction. You can tell that you're moving. But if the windows are closed, there's no experiment you can perform that will detect whether you are at rest or moving with a constant velocity. This leads to what's usually called the principle of Galilean relativity. Since the laws of mechanics can't tell one inertial state from another, it does no harm to call any state of force-free or inertial motion a stationary state. So in that sense, the principle of relativity does not originate with Einstein. He generalizes the Galilean principle of relativity. Let's come at this another way. If you and I float past each other in the depths of empty space, there's no way for us to tell which of us is really moving. We can say everything we want to about how we're moving with respect to each other. One is tempted to say that the question, which of us is really moving, doesn't have any meaning or doesn't have any empirical meaning because there's no way to tell. Hold that thought. It's a bit more complicated than that because there was reason to think that other parts of physics than the mechanics of ordinary moving bodies, middle-sized dry goods, as it were, might provide some meaning to the idea of which kinds of motion count as real motion and which kinds count as mere relative motion. In particular, the theory of electromagnetism, including light, provided some reason for thinking that we could make sense of the idea of something like absolute motion. How's that? According to the theory of the 19th century Scottish physicist James Clerk Maxwell, light is a kind of electromagnetic wave. And we will assume, along with Maxwell and the best physics of the day, that this wave is transmitted through a medium. Waves need some medium to pass through. This was called the ether. So light passes through the ether like sound is transmitted in air or in water. So let's use sound for a moment. Imagine a wave of sound transmitted through some water. If you're at rest with respect to the water, you'll measure a speed for the sound that's the same in all directions. And this is pretty much what we mean when we talk about the speed of sound in water. The speed of a wave depends only on the properties of the medium through which it propagates or moves. But if you start moving in the water, even if you're moving at a constant velocity, the speed of the wave, relative to you or as measured by you, will be different in different directions. Why? Because you'll be gaining on the wave in some directions of motion and moving away from it in others. So it's just as if someone throws you a baseball, you'll measure the speed of the baseball relative to you as greater if you're running towards the baseball and less if you're running away from it. Now, one trick here is to focus on what you would see or measure, not what you know is really happening. You can't abstract away from what you'd actually experience and talk about the speed of the baseball relative to like the playing field or something like that. That will only confuse you. So we're talking about what you would experience or measure. So far we've applied Galilean relativity to wave motion. And now we're carrying this over to light. Light moves with a constant speed through the ether, just like the speed of sound in water. Now, if the Earth, along with the rest of the solar system and the galaxy, is, as it were, swimming at a constant velocity through the ether, we should be able to detect the rate of motion through the ether by looking at differences in the observed speed of light. Just as with the case of the swimmer and the sound, we should be catching up to the light when we were moving in some direction, we here being the Earth, and so the light should appear to be moving more slowly than it would in the ether itself when we're catching up to it, and it should appear to be moving more quickly than it would in the ether itself when we're running away from it. Now, it's not automatic that motion with respect to the ether is the same as motion with respect to space itself, but it does seem like that's a pretty special reference frame, since the ether pervades all of space. Right? The ether is everywhere. Light transmits itself through everywhere. So there's no violation of the principle of Galilean relativity here. You can still treat all inertial or unaccelerated motion as relative, but light does seem to have its own special or preferred reference frame. And the reference frame in which light has a constant velocity, you might well call that space itself, or a reference frame from which you could measure absolute motion. As you might know, the experimenters could not find this special reference frame. Much to their surprise, they always measured the same velocity of light, no matter from what position in the Earth's orbit they were measuring it. And that speed of light is the speed you'd expect if you were at rest with respect to the ether. Light, experimentally anyway, seemed to be disobeying this Galilean relativity, this principle that all unaccelerated motion is relative. And this is very strange. We're a little over-accustomed to it by now. It's as if you measure the same approaching speed for a baseball, whether you're running toward it or running away from it. It's very peculiar. So, Einstein didn't discover the constancy of the speed of light. That's an apparent experimental result from the late 19th century, and it was a feature of Maxwell's theory from the mid-19th century that nobody had quite known what to do with. Einstein's contribution is not, as it were, inventing or formulating these principles. It's bringing them together. And this is a challenge because the relativity of inertial motion and the stubborn unrelativity of the speed of light sure seem like they contradict each other. Let me elaborate here. So we've granted the principle of Galilean relativity, which says it's meaningless to talk of my moving at 55 miles an hour. I have to be moving with respect to something, the police officer with his radar gun or something like that. But it does make sense, supposedly, to talk of the speed of light. In a vacuum now, we're going to drop the ether stuff because we don't need it. The speed of light is 670 million miles an hour in a vacuum. That's not relative to anything. And if I travel at light speed, chasing after a light beam that's receding away from me, it won't slow down or stop in its relative motion to me, right? It will still be moving away from me at 670 million miles an hour. So it sure looks like the unrelativity of the speed of light and the relativity of Galilean comparative motion contradict each other. And if they do, one of them must be false. Pretty much everybody was sure that the false claim was the one that the speed of light doesn't change no matter how quickly you're moving with respect to it. But the experimental data wouldn't go away. So scientists were forced to take some relatively desperate measures. One hypothesis was that the Earth dragged the surrounding parts of the ether around with it, so that the part of the ether around the Earth was always at rest with respect to the Earth. That's why you couldn't measure the speed of light's variations. Another hypothesis, a more popular one at the time, but a pretty desperate sounding one, held that the measuring devices used to evaluate the speed of light shrunk, and clocks slowed down as the Earth moved through the ether. Now, this sounds crazy. It's not quite as crazy as it sounds, because the idea was that the ether is what electromagnetic forces, light and other forces, propagate through, and if it's electromagnetic forces that hold objects together, then maybe motion through the ether would change the objects. But this is still a pretty desperate hunch, because it posits that the speed of light is changing, but we have no possible way of detecting it. We will always be stuck measuring the same speed of light, even though the speed of light, in accordance with Galilean relativity, must be changing. Einstein's genius consists of accepting all of the experimental data. And what this requires is explaining away the apparent contradiction between the principle of Galilean relativity and the unrelativity of the speed of light. And Einstein overcame this apparent tension by critically examining some of our most central concepts. What he discovered is that these principles contradict each other only if certain assumptions that nobody had formulated or questioned about space and time are in place. So the first thing Einstein does is generalize the old principle of relativity. It's not just the Galilean principle where all mechanical experiments are indifferent to motion at constant velocity. All experiments, electromagnetic, what have you, are indifferent to motion at constant velocity. So the speed of light, like Newton's laws of motion, doesn't care about motion at constant velocity. So this brings the old principle of relativity and the absolute speed of light together, but it has some mighty strange consequences. Observers moving with respect to each other will, even if all of their instruments are incredibly sensitive and functioning properly, they will disagree about such matters as whether one event happened before another event, how long an event took. So, in a certain sense, Einstein takes on the principle that measuring sticks shrink, clocks slow down, but the explanation is not that the speed of light is changing and we have to figure out a way to make the experimental data fit with the fact that the speed of light is changing. No, the speed of light is constant. Space and time are much weirder than we thought they were. The clearest illustration of this that I know of is due to a physicist named Brian Greene, so I'm going to borrow with some modifications an example of his. Two countries have been at war, and their presidents are about to sign a peace treaty. President Engine Facer and President Caboose Facer. The names have significance that will emerge shortly. But it's important, because this is a very fraught political conflict, that neither president signed the treaty before the other one does. The treaty needs to be signed in neutral territory, so the two presidents get on a train, moving, of course, at a constant velocity. And right when the center of the car passes over the border between the two countries, a light bulb goes off. President Engine Facer, of course, sits facing the front of the train. President Caboose Facer sits facing the rear of the train. Each president is equidistant from the light bulb. Each president has very good vision and very good reflexes. And each president signs the treaty immediately upon seeing the flash of light. Both presidents are very pleased with this solution, very pleased with the execution of it. But interested and very sharp-eyed observers from both countries are on the platform as the train crosses the border. And they are horrified. They insist that President Engine Facer signed the treaty first. Now, both presidents and all of their minions deny this charge. They were paying very careful attention because this was a big deal. And the people on the train insist that the signings were simultaneous. But the observers on the platform, who, like the observers on the train, are allowed to think of themselves as stationary, point out that from where they stood, President Engine Facer is moving toward the light, while President Caboose Facer is moving away from it. Let's make sure we realize why this is true. From the standpoint of the platform, the train is carrying Engine Facer toward the light bulb, and Caboose Facer away from it. All right, since it's all moving in the direction of the train's motion, the light is being carried from the standpoint of the platform towards Engine Facer and away from Caboose Facer. It's important here to focus on what you see not what you know about how things would look on the train. You have to focus on your observations from the platform. So the observers on the platform agree that the light moved at the same speed toward each president. But they insist, you have to have very sharp eyes, of course, to make this out, that the light had farther to go to reach caboose facer than it did to reach engine facer. And this is why they saw engine facer sign the document first. So one set of observers says the signings were simultaneous, another says President engine facer signed first. Well, who's right? Everybody is. That's Einstein's innovation. It literally depends on where you stand, which president you will have observed signing the document first, or whether you will have observed them signing simultaneously. Now, since both observations are correct, there's got to be something wrong with the question. Namely, when did the signing happen? It happened differently in different reference frames. So Einstein shows that such questions are meaningless, in the same way that the motion in deep space with respect to each other is meaningless unless and until a reference frame is specified. If you and I are in uniform or inertial motion with respect to each other, your clock will seem to me to be running slow. Mine will seem to you to be running slow. Of course, we have to be very, very astute in our observations or moving very, very quickly with respect to each other if we're going to make any of this out, but let's grant that. The sense that we both can't be right, it can't be the case that your clock is running slow and that my clock is running slow, that comes from the pre-relativistic assumption that Einstein is trying to help us get over. That assumption is that there's just a plain fact about when something happened or how long it took. So we've talked about time so far. Similar considerations apply to the measurement of space. Meter sticks in your frame of reference are going to look shorter to me than they will to you. Likewise, assuming we're moving with respect to each other, my measuring stick is going to look shorter to you than it does to me. Each of them can't be shorter than the other if we're talking about the same reference frame. But of course, each wouldn't be shorter than the other if they were in the same reference frame. So here, let me use another example. This one's kind of a classic from all of the relativity books. We place a pole next to a barn. Same reference frame, not moving with respect to each other. And we measure them very carefully and assure ourselves that they're the same length. But then somebody really fast, somebody who can run, 7/10 the speed of light, runs through the barn at a constant velocity carrying the pole. You and I stay at the barn and watch. Now it's going to get weird. From our standpoint, the pole has shrunk. And so we should be able to close both barn doors with the pole inside. But from the equally legitimate perspective of the runner, because the velocity is constant, right? The barn is in motion, as are we, the observers in the barn, and so the barn has shrunk. And so it should be impossible to close both barn doors with the pole inside. So we're going to run the experiment. Is the pole going to end up being shut in the barn or not? Yes, both. You and I will see both doors closed with the runner and the pole inside, while the runner, we're going to give the runner eyes in the back of his head here, will see the farther door still open and the pole poke through the far door before he sees the near door close. The trick, we don't have time to go through it in detail, and you don't need, if you're willing to take my word for it, you don't need to understand this in great detail. But the trick is to calculate how long it will take information traveling at the speed of light, right? That's the fastest information can go. How long will it take that information to reach each observer from each relevant position in the barn? The relevant positions are the two doors and the two ends of the pole. What Einstein shows us is if we actually calculate that and get over our assumptions about how we know it's supposed to go, the appearance of paradox disappears. We will see that if you just look at when light reaches each observer, you'll see that there's no contradiction here at all. Now, obviously, nobody has performed the experiment of having somebody run at 7/10 the speed of light through the barn. Doesn't mean that special relativity has not been very impressively experimentally tested. There are little particles called muons, which live, not biologically of course, they fail to disintegrate for about 10 times longer if you accelerate them to near the speed of light. Time for the muons, as measured by us, slows to a crawl. Now, fortunately for me, because I'm about at my limits with this physics, the physics is of secondary importance to the philosophy for us. The point is that other physicists assumed that they knew what they meant by a concept like simultaneous or having a certain length. Special relativity shocks us and shocked them only because we think we have space and time figured out much more thoroughly than we in fact do. Much of Einstein's achievement involves linking the concepts, simultaneity, length, very tightly to experience and measurement, and denying that we can legitimately use these concepts when they're disconnected from experience and measurement. This idea exerted tremendous influence on physicists and philosophers. And it's this idea that occupies philosophers for the first couple of decades, not exclusively, but largely, how to link our scientific concepts properly to experience and measurement. So we're going to turn to more explicitly philosophical considerations and ask in what way a concept must be cashed out in experiential terms, in measurement terms, if it's to count as scientifically legitimate. And the first major move in this area comes not from a professional philosopher, but from, like Einstein, a philosophically inclined physicist, a Nobel Prize-winning physicist named P.W. Bridgman. Wanted us to learn the lesson of special relativity, and he thinks the lesson is a conceptual lesson. So it's kind of a call to arms. Never again, says Bridgman, are concepts going to be allowed to prevent us from seeing what nature tries to show us. That was the point of special relativity. Nobody could see that the experimental data was right because they had a theory between themselves and the data, and Einstein thought his way through the theory. The way to prevent this from happening again is to be sure, when we use a concept, that something in nature answers to that concept. Now, how do we do that? Bridgman offers a view called operationalism, which says that we must define each scientific concept entirely in terms of the operations we would use to detect or measure instances of the concept. So what we mean by length for Bridgman is exhausted by the measurements we take of length. We don't mean some philosophical definition like length means taking up space. That leads to bad metaphysical theories of space. What we mean by length is, you want to know what the length of something is? Grab your trusty meter stick and place one end of the meter stick at one end of the object. And if the object is shorter than the meter stick, look for a certain number. That number is the length. If the object is longer, then you got to start over and start from where the last meter stick left off. You all know how to measure things. That's the length measuring operation. And Bridgman thinks if we confine ourselves to the operational meaning of terms, we won't get into the kind of trouble that we needed a genius like Einstein to cure us of. Had we insisted on an operational definition of simultaneity, we'd have realized that we don't have a good way of measuring it for events that are at a distance from one another. Now, if cell phone signals could move infinitely fast, then you and I could just call each other and talk while something's going on, and it wouldn't matter how fast we're moving with respect to each other or how far away we are from each other. We'd be able to agree on which events were simultaneous. But since no signal can move faster than light, there won't be any way of measuring simultaneity, at least what we thought we meant by simultaneity. And here's Bridgman's point, if we don't know how to measure it, we don't know what we mean by it. We can measure simultaneity using light signals. I won't go into the way you'd set up an experimental apparatus to do that. But if we do that, we'll realize the moral of the barn example and the train example, which is that observers moving very quickly with respect to each other can't agree on when two events are simultaneous or whether two events are simultaneous if we define simultaneity operationally. So we'd never have been shocked by this. So let's try applying operationalism more generally. Strictly speaking, each operational procedure should be identified with a distinct concept. So you've got the concept or operation of temperature as measured by an alcohol thermometer, and the different operational concept, temperature as measured by a mercury thermometer. Officially, since we're using different measuring devices, we change the subject whenever we change operational procedures. Why? Because on Bridgman's view, the procedure is the meaning. Now, this isn't a fatal objection. It's going to be a problem for Bridgman. So far, Bridgman can just say he wants us to understand that we're taking a risk whenever we identify temperature as measured with an alcohol thermometer and temperature as measured with a mercury thermometer. It gets a little worse than this because it's not clear how we should individuate operations. Very strictly speaking, using blue litmus paper while wearing a white lab coat should count as a different procedure from using blue litmus paper while wearing overalls. Right? There's something different involved in the measuring. It's not clear exactly how Bridgman's going to approach this. I assume he would say that ideally we would distinguish these procedures. We don't usually just bother or get around to doing so. How comfortable Bridgman is entitled to be with the assumption that it doesn't matter what color the clothing of the laboratory worker is when you're measuring the acidity of a liquid, that's a problem we're going to return to in a moment. But right now we're still fleshing the view out. Another thing to notice about Bridgman's view is it requires a basic vocabulary in which operational definitions can be given. What do I mean by this? Operations have to end at something that doesn't require further operationalizing. All right, so you can talk about placing a thermometer in liquid. That's part of the temperature measuring operation. Another part of the temperature measuring operation is removing the thermometer from the liquid. Another part of that operation is holding the thermometer in front of your face and looking at the scale. But we can't operationalize everything. It had better end in some kind of look and see and write down the number that doesn't itself require further explanation of what that means. So Bridgman is helping himself to the assumption, as virtually all scientists do, I'm not putting this forward as an objection, that some phenomena are directly and unproblematically observable. And so those don't need to be operationalized. There's some base level at which you can just say, look and see and write it down. And you stop there. So I'm granting Bridgman that assumption, at least for now. But we should know that this is pretty different from the conception of observation that we saw at work in Karl Popper's philosophy. Bridgman is assuming, as Popper would not assume, that there's a special language or level of observation that is available for the purpose of explaining theory, and that observational language itself does not stand in need of explanation. That when you get to the look and see stage, everything's okay. And that can be used to explain other things without itself standing in the same need of explanation. So I'm just noting that difference. We'll be coming back to that a couple times through this course. Operationalism for a while in the 20th century was enormously influential in many scientific disciplines. It continues to be influential in some, especially psychology, where diagnoses are sometimes explicitly operational. To say that a patient is depressed, to psychologists of a certain school anyway, just means that the patient scores below a threshold on a certain test. They don't want to let you mean anything else by that at all. The motivation for this is pretty straightforward. Psychology is a tricky business. It's complex. We want the terms to be regimented so everybody uses a term like depressed in the same way. And so they appeal to an operation, a test, a measuring device, to clarify, to show the links between experience and the proper use of the term. The question is whether the links are too tight. Most philosophers think that operationalism is a too stringent way of trying to tie down our concepts in experiential terms. And the problem you're going to run into, if you're an operationalist, is that if we restrict our conceptual resources this way, we're either going to cheat, we're going to smuggle in some kind of meaning that isn't operationally legitimate and assume we know what we're talking about in the way that Einstein warned us about, or we'll deprive ourselves of meaning we need in order to do science. We'll see some problems with this whole approach a little later. Right now I'm just focusing on problems with the specific operationalist version of the approach. So let's try to operationalize weight using a pan balance. All right, so place something on this side, place something on that side. If they have the same weight, the pans will balance. whichever one falls lower weighs more. This assumes that there are no additional forces acting on the pans. Right? If somebody's got his finger on one of the pans and pulling down, that's going to throw off the measurement. But how can you operationally specify there are no additional forces operating? You can build in a check and see if anyone has his finger on the pan balance operation. You can build in the check and see if there's a magnetic field operating on the pan balance operation. If you can explain these in operational terms, you can build them in. But there are going to be a gazillion such possibilities. It's hard to shake the idea that what we mean by weight isn't whatever the outcome of the pan balance is. We've got some idea of what we mean by weight that the pan balance is supposed to be tracking, because otherwise we wouldn't be able to rule out all of these other factors from influencing what the pan balance reads. A similar problem is going to arise if you identify the outcome of two different operations, like using litmus paper wearing a lab coat or using litmus paper wearing overalls. Our confidence that the two different kinds of thermometers measure the same stuff tracks this idea. It's also tracked by the idea that there are changes in temperature that are too small to measure. The idea that temperature is, as it were, out there, being tracked by these operations, not being constituted by these operations. So, one last illustration. If you tried to use a thermometer on the surface of the sun, it would explode and you would die. We can try to figure out how to build a device that would accurately measure temperature on the sun. But there we're using the notion of an accurate temperature measuring device. We're helping ourselves to a notion of temperature, and we've given up on reducing the notion of temperature to what we can actually measure. But that was supposed to be the point of operationalism. The point of the Einsteinian revolution was supposed to be you can't help yourself to content that runs beyond measurement. So Bridgman, under the influence of Einstein, is onto an attractive and important idea. As we'll see next time, this general idea has a long philosophical history, and we're going to see how philosophers had for centuries been responding to these issues that physicists had just now made newly urgent.